Great, so.
Pardon me.
Silence yourself.
Yes, exactly.
Okay, so the plan for the talk is I'm going to tell you about some of the techniques behind some of these follow-up works that I had with these co-authors, Amir Aboud, Nick Fisher, Shahar Levet, and Raghu Meka. Actually, a lot of these, these are follow-up works to my work with Raghu Meka on the 3AP problem, which I'll define in just a second. And something I think is interesting is really a lot of these follow-up works are in pretty substantially different domains. The actual application are like in some cases they're about extremal combinatorics, sometimes they're about communication complexity, and then one of them is even about like triangle detection algorithms for graphs. And really the thing that's common to them all is the tools. So that's what the talk is focusing on, like the tools rather than some application. But I will tell you, just in case you haven't seen it before, the background, like the context as in, we'll talk about like what is the 3AP problem and what did we prove regarding it. So maybe I'll start here. So this problem is related to some famous question due to Paradosh, 1936, and he asked following questions. So let A be some subset of the integers 1 through n, and the only thing we assume about A is that it's somewhat large. Size of A is at least delta times n. And the question he asks is, what value delta is sufficient to force A to contain a 3-term arithmetic progression? Okay, so that's just draw what I mean right here. Just some triple of 3 points that are evenly spaced. So maybe add a few extra points. Maybe here's our set A, and then I'm looking at some points A plus D, A plus 2D. So this is exactly the configuration that we are looking for. We're asking whether, just by virtue of A being very large, does that force this pattern to occur somewhere within A? And yeah, the question is to determine the value delta for which this is guaranteed to happen. So let me tell you some upper bounds. So in the 50s, Roth proved that if any set has density larger than roughly 1 over log n, then that's sufficient to guarantee the existence of one of these patterns. Some non-trivial 3-term arithmetic progression. So this is notable for being like the first bound that goes to 0 as n goes to infinity. And then since then, there's been really a bunch of works, which I won't try to write down all of them, but it's really like a very well-known problem. So it has had a lot of quantitative progress to this delta. People like H. Brown, Samaretti, and Bourgain worked on this. Then let me write down this result due to Sanders from 2012. Got very close to some like 1 over log And actually, I'm hiding some log n factors in the numerator here. But this 1 over log n threshold is like an important barrier both for technical and aesthetic reasons. I guess I'll say a bit about that in a second, but the first to break this barrier so work by Bloom and Sisas pretty recently, actually, and just 2020, and they improved this log n by some, like, they get some 1 plus some small constant c in the exponent. So getting slightly past this 1 over log n barrier.
Is there a lower bound and delta?
Yeah, so I will, there is, and it's very far away from all of these, actually. So I'll say what's known about that in a second. Yeah, this isn't a barrier because it's close to the lower bound. It's like for some technical reasons, I guess, and then, like I said, also some historical reasons. So, in fact, there's a conjecture by Erdős, which, okay, there's a cute way to phrase it, which I'm not going to try to write down, but he's asking whether a set contains a KAP just if this delta is like little o of 1 over log n. That's his conjecture. For every fixed k, that should be true. So I mean, this doesn't quite prove this, and then this does prove this. So this is the yes, for k equals 3. So for the first case of this conjecture, and one notable reason for this is that's roughly the density of the primes is like 1 over log n. So you could, and then well, it wasn't known when you made the conjecture, but it's known now. It's like the Green-Tau theorem that the primes contain arbitrarily long arithmetic progressions. And you could ask if that's true just by virtue of their density alone, like nothing, using nothing about the structure of the primes specifically, just how dense they are in the integers as n goes to infinity. It's plausible that that's true just by virtue of their density, but that's not known how to prove that yet. Anyway, okay, so this is the result prior to our work. So in 2023, we proved this. Well, actually, maybe I'll come back to this. I'll talk about the lower bounds first. So let me talk about a very easy lower bound first. So if you pick a random set A and just use, like the probabilistic method. So there's only so many of these patterns. Like you could just fix every A and every D and then just try to check, how low do I need to set delta so that it's likely that a random set of density delta is going to have no 3 APs. So for that, it's easy to check that you can set delta to be, roughly into the minus 2/3. So this density, I'm going to be calling this polynomial density in this polynomial in n. And very interestingly, something that sets this apart from a lot of other like forbidden configuration problems is that this is actually not very close to the right answer. So there is a construction due to Berend, which gets this funny looking density. So he gives an infinite collection of sets which are somewhat larger than these random sets, but somehow still they contain no 3-term arithmetic progressions. And this is some like algebraic or geometric construction, you could think. Yeah, and I think this is fairly notable for being like, for example, if you're used to like probabilistic method arguments having to do with error correcting codes, for example, and then you ask some sort of similar question where, how can I avoid some configuration like 2 points that are close? Then often like the random choice is roughly optimal for these kind of questions, but here it's not. So Berend gets this density lower bound. Throughout the talk, I'm going to call functions of n that look like this, quasi-polynomial in n, which is maybe unfamiliar, but that's just how I'm gonna refer to this funny looking function. And so our result is that we got the first kind of quasi-polynomial shape bound. Now we don't get this, get a different exponent. So it's open to try to get it all the way down to Barron's lower bound. We prove it with this quasi-polynomial with some different constant like 1/12. Any questions so far?
So I'm a bit surprised at the random bound that you gave.
Oh,
Isn't it 1/√n?
I mean, I see, like, I was running a very cheap argument, so maybe it's not the best you could do.
This is genuinely just no. I guess at this point you don't get any immediately, right? This is without removing anything. Any
Yeah,
processing.
yeah, you're saying, yeah, okay, what, sorry, maybe I should be clear, yeah, this is not optimized at all, this is like the cheapest argument you can write down to get some, so fine, maybe you could ask what happened if you optimize that. I don't think you'll get close to quasi-polynomial.
No, you get a
Yeah.
polynomial bound.
Yeah,
But I also think it's better. It doesn't matter.
No, it's not important.
Okay.
It's just your bounds, of course, is important.
okay. Yeah, so let me say a bit more about what we specifically prove. So, I mean, this isn't special to our work. Most of these works that at least focus on like, the so-called analytic method to this problem, they're not just finding one through AP, they're finding many of them. So we're just trying to count the number that we see and give some reasonable lower bound. And yeah, specifically we get some theorem of this shape. So here I want to call attention to this. Yeah, we're looking for solutions to this linear equation. So just make this clear what the connection is. Like if I have 3 points, I can just ask if they satisfy this linear equation, and that tells you exactly when they are in this pattern, when they're a 3p. Like if I have this x here and y, and I'm asking if z lies exactly at the midpoint of x and y.
How specific is your, oh, sorry. You have to, how specific is your method for this equation?
Oh, yeah, so I think it's not very specific. That's how I would say is I think I can give you a bit more detail about why that is in a second, I guess. There are some like technical issues that when you're talking about like the integers or the cyclic group, I think that, I mean, it matters that this 2 is small, at least a little bit. I think that might actually be necessary, but like, for example, I'll say in a second too, the method is fairly general. It works for dense subsets of any like finite abelian group, like vector spaces over finite fields. And there it really doesn't matter what coefficients you have in these kind of equations.
Yeah, but for finite fields, better bounds are normally realizable.
Sure, that's true.
The answer is not, it was polynomial.
Yeah.
It is polynomial.
Yeah, that's right. Okay. I was saying that, oh, okay, so these are counting 3 APs plus something a little bit annoying is that it also counts the trivial 3 APs, right? So if X and Y and Z are all the same, then it gives you the trivial 3 APs, but right, there are all at most n of those. So you know, by getting this bound and then setting D to be something reasonable with respect to n, then this guarantees at least some non-trivial 3 APs.
Many.
Well, sure, many. So this is, yeah, the form of the theorem that as we prove it. And then I want to say, like, what is the approach? So it's being somewhat vague at this point. So the approach is by like this structure versus randomness paradigm. And say more about what I mean by this in a second, but to begin with, something I definitely want to start by doing is like taking this and reformulating it sort of trivially as some kind of probabilistic statement. So let me start doing that. So I'm going to let X and Y be two independently sampled uniform random variables coming from our set A. And then define this set Z here, which is just 2A, again, like this dilation of A by 2. Okay, so, yeah, like a somewhat trivial reformulation of what I want to prove is that the probability, you draw X and Y randomly from A, look at their sum, you ask what's the chance that that lies in Z, and I want to prove that this is something like this quantity here, some quasi-polynomial in our density parameter, this little d, which sometimes I'll refer to as the entropy deficit of A. Okay, so far that's not doing anything interesting, just how I'd like to think about it. And yeah, I want to say, so what's going on with this structure versus randomness approach? The way I would like to think about it is, this is something that's generally reasonable thing you can try when like a typical set A, like a random set A, is actually not a bad example. Like you want to reduce to like the typical case where A has mostly, you know, some random or pseudo-random structure. You remember we checked up here that a random set A should be fine. Like it gives us as plenty of 3 APs, as many as we like to, you know, in light of the fact that I'm just trying to get some quasi-polynomial bound. So with that in mind, I want to like define some sort of notion of pseudo-randomness. That's it'll be capturing some sort of additive pseudo-randomness of the set A, and it'll be something that's just designed so that if it holds, then I see roughly as many 3 APs as I would if A was like a random set. Okay, so let me do that over here. So when do I want to say that A is pseudo-random? So that say A is pseudo-random if this random variable X plus Y is near uniform. Yeah, sorry, maybe I should comment on this for 1 second. So in our paper, we dealt with this case that A is like in a cyclic group, and the like you could think the other extreme case where A is in a finite field. But actually, a nice follow-up work due to Bloom and Cis-S got the argument running just generically inside any finite abelian group. So it's yeah, they have some nice approach that kind of cleans up what we were doing and works in all finite abelian groups at once. And yeah, I just want to say that here, nothing about what I'm going to tell you is very specific to the case of a cyclic group or even like a finite, that it applies to like vector spaces over finite fields or other finite abelian groups. So I just want to say that it's near uniform. So let me draw a picture, a bit more specific.
Do you need to work modulo n, or can it be in Z and still have this theorem?
Yeah, so you do if you want to frame it like this, but like there is a way to kind of, so yeah, so what do I mean by this? So let me, maybe I can draw, I don't want to.
There's no totally follows from this thing.
Oh, the statement itself, yes, but I thought we were talking about, we're talking about.
Yeah, but you have many. Yeah, you have enough.
Ah, sorry. Okay, you're asking whether the statement itself. Yeah, so the statement itself is fairly like the question is roughly equivalent, right? If I just take my set A and then, right, okay, you might have to change n to like n prime, which is like 3n or something. And then you can kind of, yeah, okay, so it's not like a direct equivalence, but yeah, it's like some approximate equivalence. Okay. For this particular definition to capture when A is pseudorandom, it does somewhat matter that we've decided to go to embed in like a finite abelian group. So I want to look at this probability density function D. So this is the probability density function of this random variable, y. Here's like the uniform density function, and
The parameter to how pseudo-randomness.
yeah, we'll talk about that as yeah, we'll talk about what we need.
Go ahead.
That's like exactly what I'm doing, right? So yeah, so let me just draw. So what do I mean by near uniform? It's going to be parameterized by, I guess, two considerations. One is this, band in the y-axis that I would like my probability density function to be roughly equal to 1 plus or minus some fixed like absolute constant epsilon. Okay, but then maybe I'll also allow it to fail to be that close on some tiny region. So some bad set of points that's like maybe, yeah, so I'm going to write down this other number p's, which is quantifying how often you fail to be this close to uniform. And we can think about like, what do we need to set p and epsilon just so that we get what we want, okay? Because we're designing a pseudo-randomness condition that's good enough to get what we want currently. And so, for example, if you set epsilon is say 1/2, and then maybe p is d plus 1, then we do get what we want. Then this probability that x plus y lies in some set z is at least 1/4 times 2 minus d. So certainly this is plenty sufficient. So what I'm saying something sort of trivial here, just that if I set the p to be this small, and then I look at an arbitrary set, maybe I'll draw it here. If this is my set z, then only half the points that lie in z are bad points. So and I'm at least getting like half the contribution that I would hope from like a random set. So I'm gonna get this many, or like, yeah, this chance here with the factor D even. So this is like easily sufficient for what we like. And then
Set Z, which is set A, which is measure 2 to the minus B.
yeah, right. So yeah, so I've used that as well. So that's sort of the only thing I've used about Z, and that's why I wanted to say, at least in a vague sense, like many of the techniques that we have are not very specific to this equation here, right? Because I'm just looking at the PDF of this random variable, and then this 2 times Z is just playing the role of some arbitrary set of this size over here.
But I'm sorry, can you repeat that? The definition of near uniform?
Yeah, so near uniform. So so what do I want to do? I want to take X and Y, both independent and uniform from A. And then I consider this random variable, the sum of X plus Y. I look at its probability density function. I'd like it to be near uniform density function, where I quantify that with some like multiplicative error here in the y-axis. And then, so I would like it to be within, okay, so I'd like D minus 1 to be at most epsilon, except for on some tiny fraction of points, which is quantified by P.
It tells you in particular the image, like X plus Y. So A plus A is almost.
Oh, yeah, sure.
15.
Yeah, certainly that's also true.
Okay.
Yes, that's also true. Yeah, so maybe I need to say one more thing about this and I want you to just trust me on this, or you can do some math yourself if you like, but I like thinking about this near uniform condition in this like epsilon delta formulation, but really often we need some roughly equivalent way of capturing this condition, which is just that this p norm distance to 1 is at most epsilon. So you can either do some calculations yourself or just trust me that this is approximately the same. Save one more. Okay, so what's the point here is that in some sense, this takes care of most A's. Like most A's will have this property, like a random choice of A will be near will result in this density function D being near uniform. And like all that's left is to think about how to deal with like the special kinds of A. So very vaguely, let me say, how are we doing that? So this structure versus randomness heuristic, I want to call it like this because it's true if you interpret things right in like a pretty wide range of settings. So any dense enough set should be pseudo-random somewhere. Okay, so I state this pretty vaguely because it's kind of generally applicable for wide range of situations, like dense subsets of any sort of space with almost any kind of definition of pseudo-random. Yeah, okay. So let me talk about like specifically what do I mean here. So can anyone tell me an example of a set which would fail to be pseudo-random according to this definition? Like just some easy example.
Constructed as you mentioned before. by switching to n prime is 3 n.
Yeah, so that would work, right? Okay, so yeah, if we do this and then if A was just anything, now this PDF of x plus y, it's just only distributed on this first, what, 2/3, I guess. So here's 1 and so yeah, that's an interesting example. Just even if A was pseudo-random to begin with by like changing the space. Now, yeah, so I agree.
Take them to be even, or
Sorry?
you just think things to be even, you're never gonna get an odd.
Yeah, that's also a good example. So, okay, so maybe I'll write that down as well. Yeah, so you could take A on this interval to only include even points. So points inside 2z. And certainly this is like a, some subgroups, so it's closed under addition and yeah, when you take this convolution of A with itself, you're not going to see any odd points. So certainly that fails badly as well to be near uniform. So yeah, so what's the point? The point I want to make about like both of these kind of examples is that the reason they fail to be near uniform is because they're kind of concentrated on some very structured, like additively structured subset. So as long as we zoom in on some additively structured container set, then we can maybe hope for the set to be pseudo-random relative to this container set. Could hope to just do that always. So I'll just draw. This is like the picture. This extreme version of the picture I'm thinking of is maybe the PDF of A looks like this. And all we need to do is zoom in here and then, A wasn't pseudo-random on the whole space, but once we zoom in here, it's pseudo-random relative to this container set. Okay, so.
Container still has many elements.
Yeah, so certainly at the end, so we're paying something. So at the end, we wanted to count as many solutions as we could get. So if you have to zoom in somewhere and it's very small, then you're giving up something here. So we would like to zoom in on some new universe that's not too much smaller in order to obtain this pseudo-randomness condition. Okay, so.
Maybe I can make a general remark you probably didn't plan to, which is a bit of the slide, but this convolution x plus y of a large set over a group, especially over simple groups, non-abelian groups, you don't have these counterexamples. And the fact that they become uniform over these groups as it's called groups which have this property are called quasi-random groups by Gauss, and this property is used to prove big results like that every simple group expands with a constant number of generators, even if with a random pair of generators. So it's but there you don't have this counterexample. Yeah.
Yeah, I think that's interesting. Yeah, so in some groups, they just any set would satisfy this pseudo-randomness.
It's a much smaller set.
Yeah, even fairly small sets. And maybe I'll save that aside for later. But okay, let's see. So okay, I'm not going to get into too much detail about how we finish the rest of this plan. I just wanted to motivate this general setup because we're going to talk about some techniques. But let me just I will give you a name for. So how do we finish this proof that approach that I've sketched here? So what are the ingredients? So. Say that there's one ingredient, which maybe I'll call it translation invariance. Or you're familiar with it, that's roughly, I just mean the crude success lemma. And then some second ingredient called sifting. It's related to, if you're familiar with it, dependent random choice. And some third ingredient called spectral positivity. And the plan for the rest of the talk is to talk to you about how, I mean, something that wasn't really appreciated at the time that plays an important role in all these follow-up works is that these techniques 2 and 3 are actually better thought of as some sort of general techniques for studying dense bipartite graphs, have very little to do with the group structure involved in this problem that I set up. I mean, this ingredient 1 has very much to do with the group structure. But like that's not really where our main innovations were. They were mostly related to the second points. So I'll tell you a bit more about how this applies to this specific problem maybe at the very end, but for the rest of the talk, I was going to focus on some like just, some graph-theoretic point of view and discuss how I view both of these techniques in like a more abstract, just combinatorial sense. Okay. That's maybe the end of the preamble. I can stop if there's any questions so far about the setup.
Actually, maybe I do have one question.
Sure.
So you switched to this question of finding many solutions, which of course implies the one solution. But you mentioned at some point the heuristic that if I want to find a small number of solutions, the example would look like approximating one with no solutions. Is that a fair? Is that a fair question?
No, I misinterpreted.
I feel like I'm not making myself clear. So is it true that if I have few solutions, that I should be similar to one with no solutions, or might it be that if I allow myself to have some solutions, I might look very different?
You're saying, is there like a stronger lower bound to this kind of question than the barren bound, maybe? Is that the kind of question you're asking?
I don't think that any of the techniques known in this field can generate a situation where you have few but not zero. They always, if they give you anything, they give you many solutions. In particular, more than the number of trivial solutions. More than that.
Depends on your
We
definition.
can prove that there is one. I don't know. I mean, of course, you may. That's my knowledge.
What's your definition of many?
Say one. I mean,
The reason that you kind of always get n squared is because I can kind of like randomly pass down to a subset that's an arithmetic progression whose size only depends on delta. You get at least one there, and then by an averaging argument, you get at least n squared in the high level. So like as soon as you get any bound, you immediately get at least n squared, no matter like just as a black box of like the at least one.
Because you're supposed to be resilient to like removing points.
yeah, it's resilient to branching and arithmetic progression in a small, take any smaller set with the bounded no branches, remove points.
Right.
No technique that I know.
So I'm not sure if this is very related to what you were interested in, but something I can say is that you could ask like, what's the best lower bound to this sort of statement? And I think it's still, I mean, this isn't immediately obvious, but it's still the same kind of shape, like that using like some Barron's ideas roughly, I can write down a set, like for any choice of D, I can write down a set of this density, which has only this many solutions to this equation.
I see.
Yeah, let me start by saying maybe a tiny bit more about like the general structure versus randomness. I don't know what you'd call it, like maybe, okay, this, I'm gonna paint a picture. It doesn't really encompass the method, but it seems like it's sort of involved in most of the uses. So let me just say how I'm thinking of how these types of arguments normally go. First, you're gonna have some like strong pseudorandom conditions. So for example, here, like the one we discussed, I'm saying I would consider it this kind of pseudorandom condition. It's strong, like it's like application dependent, but it's sort of, you wrote it down specifically so that if you had it, that would be useful for your application thing.
It's important that you call it x plus y instead of d at this level of this.
No, I mean,
So
sorry, this
it's a bit-
is an example, but
I know,
so,
yeah, but
okay.
what you're going to say will apply to any distribution.
Well, D is not A, like it's a pseudorandom condition on A, so on a set A.
Oh, on the set A.
Yeah.
Okay, fine, yeah. Okay. So then fine, yeah, right, but.
Okay. Yeah, this is just some
Yeah,
example.
yeah.
So you have some strong pseudorandom condition, and then on the other side, you'll have some like weak pseudorandom condition. I won't offer an example for this quite yet, but the point of this is it's something that you defined because it was easy to get. Like you can, for example, zoom in somewhere in order to actually achieve this pseudorandom condition locally. Okay? And then like this is like also application dependent, and then somehow the way I see it is like the real essence of the subject, like the heart of it is just proving that, this is secretly good enough. Okay, like maybe you have a couple more intermediate pseudorandom conditions, and somehow you want to show that your pseudorandom condition you can obtain is actually turns out to be good enough to imply the pseudorandom condition you need. Okay, so that's just how I want you to organize the rest of this talk, because mostly we're going to be talking about some different pseudorandom conditions and how they relate to each other. And the reason I'm saying that's important is because we're carrying out what I view as like the heart of the subject is like connecting weak pseudorandom conditions to strong ones. So let me start by writing down some graph-theoretic pseudorandom conditions, and I am going to start with what I think is probably the most well-known, just capturing whether your graph is an expander graph. So we're going to be talking mostly about bipartite graphs. And I'm going to write down this condition. I'll say is capturing whether your bipartite graph A is an expander. And this condition is just like this familiar form of the expander mixing lemma. for any set S on the left and set T on the right, you look at the number of edges that go from S to T, it's divided by the total number of edges in your graph, and then subtract the fractional size of S and T. And I want this quantity to be most epsilon. So specifically by this, I mean just the size of S over X. Okay, and then for a little while, I'm going to kind of insist on drawing a bipartite graph in two ways, like two different representations. So another way that you can represent it is by its adjacency matrix. And in fact, I should say something which is a bit of a warning that I am sometimes thinking of this bipartite graph A as like a Boolean adjacency matrix. And I am sometimes thinking of this bipartite graph A as a function from X cross Y to 0, 1. And then I am even sometimes thinking of this set A as just a subset of this product space X cross Y. And I will very often forget to distinguish these, the difference between these things out loud when I'm talking. So I apologize for that. That annoys you. But let me say, like, restate this condition over here. So here I'm looking over all combinatorial rectangles. So that just means some subproduct set. Take some S on the left, or some subset of rows S, subset of columns T. And right, I'm counting the fraction of A that lies in T, and I would like it to be roughly like what you would expect for a random set, up to some small error epsilon.
So one way to form such a matrix from your arithmetic story is to take A to be what it was, and the error X plus Y will be in the matrix. We'll have a 1 if X plus, when you add them up, they are in 2 with Z. Well,
Yeah, I should talk about that. So that's a good point, that the connection between the arithmetic setting and this bipartite graph-theoretic setting, I guess I like to think about it like this the most, that I'm looking at like this matrix. It's like the indicator matrix of the Kelley graph of A. So, yeah, and then so small spoiler is that the pseudo-randomness condition that we're aiming towards, we're going to be trying to compare all these things with something called the grid norm. So it will be sort of helpful, I think, just for notation reasons to shoehorn all of these other pseudo-random conditions into something I can express with some norm. So I'm going to just write down a way that I can capture this condition 1, the expander mixing lemma condition, using some sort of rectangle norm. Just like a more analytic way of describing what's going on. So here, I just want to think of some function, express 1. And right? Okay, got it here. So then with this in mind, I can restate this same condition with this notation. So here, and just asking that like this rectangle norm of A over its density minus the uniform density function is the most epsilon.
This is also called the cut norm, right?
I think that is something, I think it's essentially equivalent to it. That's something slightly different. It's like the test functions are like, like,
Yeah, but this is honest.
okay, sure, I mean, fine, okay, yeah, in that case, yeah, you get some sort of norm where the witnesses look like this instead of look like a rectangle, but sure. Yeah, I agree. And then, so my first sort of variant I want to define, it's going to be related to this rectangle norm, but it's going to be defined to be like a more multiplicative condition. Or yeah, the difference will just be in how we're measuring the error. We're going to care about like some multiplicative condition on the error instead of this, I'm calling it like an additive condition on the error. I'll show you what I mean in 1 second. And for now, let me just say that like, what's the point of this thing I'm going to define? The point is it's like the strongest condition I know that I can ask for in some pretty broad range of context. Like I can just have this, okay? So it's obviously interesting to write down what's the strongest thing you can just have and then see what it implies. Yeah, so let me write down this condition. So I'll say something. Related to this expander mixing lemma condition, but I'm going to measure the error multiplicatively. So specifically, I want this to happen. So for all large sets, S and T, specifically sets of fractional size, which is at least 2 to the minus p, I want to have this upper bound condition. Let me stop and compare with this expander mixing lemma condition. The main thing that's interesting is that we have some factors mu s and mu t over here on the right. So I would say that that's like the first important difference. The second important difference is that it's now only an upper bound, right? Now, like in the regime where you care about the additive error instead of the multiplicative error, the difference doesn't end up mattering very much. So it's like a good exercise to show. Oh, I don't have the notation yet. I'll say this when I write down some notation, but yeah, if like p is equal to 1, I want to say that this condition is like, you know, roughly up to some constant factor change in epsilon, the same as before. Which, I mean, it's not, I think, it's completely trivial, but not too hard to show either. But yeah, somehow the reason it's only an upper bound condition is that's all I can really ask for. I just don't know how to get the lower bound condition in very generic settings. I can only really establish the upper bound, and it's going to cause some troubles because it'll be a long time until we're able to prove any kind of lower bound control on anything, just because we're only assuming like an upper bound type of condition. So it's important, obviously for our intended application over here that we're trying to show that this density function D doesn't go below 1 very often, but we're starting really with only some condition on something that's saying that something doesn't go above what it should be very often. So anyway, that's going to be important for later. What else do I need to write down? So let me write down a picture again. A. And it has some like global density delta, and then for any reasonably large subrectangle, it'll have some local density delta prime, and for the condition to hold, I want this to be at most 1 plus epsilon times delta. Okay. And yeah, maybe switch these. Okay.
You just lift the low and then push the.
1 second.
But also a speed.
Yeah, but
So let me write down right here. So we compare them directly. I'm also going to write down some other sort of rectangle norm for this like multiplicative version of the rectangle norm. So. Here, this would be some max over only the large sets. And now we're going to look at like the local density. On this rectangle defined by S and T. And then, okay, so here's my restatement of the condition 2. Using this multiplicative rectangle norm, it's just asking that A so I'm just asking that this rectangle norm of A is at most 1 plus epsilon times the 1 norm of A. So this is like the same thing as the density delta that I've been writing up until now, but sometimes I'll prefer to write it like this. Okay, so here's our multiplicative version of this pseudo-randomness condition involving the rectangle norm, and then I guess, yeah, I should say out loud that when this holds, I'm saying that A is spread with respect to large rectangles. So yeah, the reason for that terminology is, I guess, in this picture here, it's not like heavily concentrated on any particular rectangle where you would have some like local density delta prime, which is much larger than delta.
You said before that this is supposed to be a condition that often you can just have, right? So for example, in the sets, like in the first part, like, can you, like, is this something that you can just have, like?
In fact, so I have some commentary about this exact point is my next thing. And so maybe I should say this, and then if you'd like know even more, you can tell me. But yeah, so that was the next thing I'd like to talk about, right? So I want to clarify a bit about this claim that like spread subgraphs are easy to find. So specifically, I just mean if you have some reasonably dense bipartite graph A, then there's some like induced subgraph that you can zoom in on where the restriction of your subgraph to this new space is spread, like it gives you this pseudorandom condition. And in fact, there's a pretty easy argument why. It's like some like local kind of greedy argument. Maybe if anyone would like to guess that wasn't at the Princeton talk, how you might be able to do this.
So if you,
If you have a violating S&T, just like restrict to it.
Yeah, exactly, right? So yeah, so let me, so if I just have my arbitrary set A, to start with, it has density delta, which is like 2 to the minus d. Okay, and then if there's any witness which violates this condition here, then why don't we just look at it to start with? So we have some S here, some T here. And when you zoom in here, so what do you win? You win some density increment. So this density is, right, at least some delta prime, which is at least like 1 plus epsilon times delta. Okay, so it's not clear what you've won yet, but I want to try to just continue this as long as I can. And if I find another violating set, then I zoom in again and I get some delta double prime, which is at least 1 plus epsilon times prime. And eventually, after doing this enough times, it won't be possible to find any more increments just because your density is bounded above by 1. So by doing this iteratively, maybe I should write down just what you exactly find by doing this iteratively. So inside any given bipartite graph A, we could find some subset X prime over here and Y prime over here, where the restriction of A to X prime cross Y prime is spread. And also, like we've been saying, that an important condition is we know that X prime and Y prime are not too tiny, so we can get this kind of bound on their size. There are at least some 2 to the minus p times d over epsilon, for example. Okay.
then
Are you happy with this, or?
I'm happy, but I have a follow-up.
Sure, yeah.
When you say easy to find, this is existential, right?
Yeah, so that's true. So in fact, for one of the applications, it is important that we can like run this algorithmically. And I agree that solving this optimization problem, I don't know if it's easy. I think it's not. Maybe Jan can tell me. Yeah, okay. But we have some other tool that we're going to get to called the grid norm, which is actually ostensibly like a bit of a stronger pseudorandom condition, but it's going to give us an algorithm for approximately, like we're getting, all these parameters like P are negotiable, so we're going to, we're not going to solve the problem exactly, but we're still going to be able to zoom in to like carry out we're going to get the same end result here, that we find some spread subset algorithmically. So I agree, it's not clear how to do that yet. No.
Should I think of it as you have some algorithm that works in, under some conditions, and in the failure condition, you somehow find a way to increment?
Yeah, well, what are we gonna do? I guess,
Okay, I guess I'll let you get to it.
okay. If you'd like to know, I mean, I can tell you, it's gonna end up being sort of related to dependent random choice, if you're familiar with that, but there'll be some like algorithm for actually finding these subsets, X prime and Y prime. And the algorithm is roughly, well, for example, you can try to pick X prime, which is a subset of rows. The way that you actually find that is you take a bunch of random columns and like take all their intersections. And then that'll give you like a good candidate for some X prime. So get to that in just a second. Yeah, that's like a.
I think the parameters are very important. These are P and Z, which are some powers of fractional powers of logarithms. It doesn't work. Right? I mean, that's what you use it for. The P may change polynomially in this
Oh, sure.
and stuff like that.
That's also true, yeah. Oh, you're saying for hardness, they're very important? Yeah, I agree with this.
Yeah, I think in general, I mean, I think the major change in your work with Raghu was that then people could only deal with much denser, let's say.
I guess, well, let's. Are we supposed to take a break?
As you wish, it's up to you.
Yeah. It's been an hour, so if you want to take a break, it would be.
It would probably be the best time, so yeah, maybe. Third formulation is maybe the most symmetric. Maybe you should take this as the definition, I guess. So I haven't written down the norm yet. This is just some quantity. To get the norm, I need to take absolute values and take some power in exponent. Here we have the actual grid norm. F ULK is this guy. Is power 1 over L times K. Okay, so let me draw a couple of pictures. So what is this thing doing? So if F is just the indicator function of some bipartite graph, one example of what is this thing measuring is, say we take 3 random test points on the left, x1 through x3, and then like 4 random test points on the right, and draw this complete bipartite graph between all of these points, and then we check if this thing is in our graph. And that's like going to be this quantity, and then the actual grid norm would be that quantity to some normalization in the exponent. Or maybe I'll draw one more picture. Maybe this is the picture which justifies the name grid norm the most. That we're just taking some 3 random rows and 3 random columns, and we check if A has all of these points in this grid. Okay. Maybe I need to keep this board.
So you mean the original points, right?
Yeah, the original, these additional dots are.
Sorry, yeah.
Are not there.
Yeah, no, they're not there. I was just- Okay, fine. Okay. Yeah, they're not there. Okay, so the grid norm, I guess I want to think about it as, well, actually, maybe I should say some basic things before that, sorry. Okay, so about the grid norm. So here are some uses. So one is, it's good for capturing certain kind of double counting arguments involving dense bipartite graphs, for example, like dependent random choice. So one example of this is, I've gotten a request to elaborate on this by Avi, which I might be able to do near the end. There's some lemma 7.4 from Gowers' work on the Simonyi theorem, where he proves, well, he's actually, this lemma is some like precursor lemma involved in the proof of a theorem that eventually became known as the Balog-Simonyi-Gowers theorem. And this is just some sort of combinatorial lemma, and it just implicitly involves this quantity U25 of some bipartite graph. He didn't phrase it like this, but that's how you can look into the proof and see that this quantity comes up naturally, and try to talk about that at the end if I have a bit of time.
If you don't, there is a beautiful survey of Benny Sudakov on this method of dependent random choice and lots of applications. Really beautiful.
And then, okay, so secondarily is that this is going to provide some sort of measure of pseudo-randomness. So specifically, I want to consider this third measurement of pseudo-randomness of a bipartite graph, which is just that this grid norm is in most 1 plus epsilon times the 1 norm. And yeah, so at this point, it shouldn't be, I think, too clear like what is good about this pseudo-random condition, like whether it's easy to obtain or whether it does anything. We'll talk about that in a second, but small spoilers that we're going to be able to show that it's sort of roughly equivalent to this condition here, but maybe a little bit more useful to actually have this than the spreadness condition, which is maybe a bit surprising.
For graphs, for matrices which are Boolean, can you characterize the case that this norm is 1?
That it's 1.
Yeah, which matrices make it 1?
I think only
the
the,
worst. They are the worst. The only one is a full matrix.
I think so, right?
Yeah.
Okay. Although that's not exactly the worst, like right, because my pseudo-randomness condition is I want to
Yeah.
measure, okay, yeah. Okay.
No, it's not the worst, it's, yeah, it's almost, yeah.
So those are some uses, and then here's some properties. So this first one's a very trivial property, but I just need to write it out to make it, to draw your attention to it, that this like U11 norm, it's just the same thing as the one norm of A, which is like just the density thing. And then we have some monotonicity. So for example, if K is smaller than some K prime, then the grid norm involving ULK is less than or equal to the grid norm involving ULK prime. Of course, like symmetrically for the first argument as well. And yeah, this has like an easy proof just by, you know, I guess by either Holder or Jensen's inequality using this first formulation. All we're doing is using some convexity to prove this. Something that's important here is that means like this condition always makes sense. Like this ULK is always larger than U11. So when you have this inequality being tight, that's actually giving you like what am I trying to say? I'm saying it can't be the case that this thing is substantially smaller than or that it's smaller at all than this over here. You're always going to be off by some factor 1 plus epsilon, and we just want that factor to be as close to 1 as possible. Okay, and then yeah, so here just some fact that justifies the name. So if L and K are even, then it actually is a semi-norm. So what I mean by that is just that it satisfies a triangle inequality. So I'm going to call it a norm, even though it's a semi-norm. It's kind of a typical abuse of language in extremal combinatorics, I think. Anyway, yeah. Oh, and this is shown by Hamed Atami like 10 years ago, actually. He just was kind of a surprise to me to see that like we defined this sort of and then went around asking if anybody had written anything down about it, and he just had. So yes, so he has some papers verifying that this is a semi-norm when L and K are even. And then, okay, so this is maybe one of the main points of it, and it's related to this relationship with this rectangle norm. So I'll just say it vaguely, but this grid norm, it can detect rectangles. Say what I mean by that, 1 second. I think I would like to leave that board alone for a little bit longer. So any questions just about the definition of the grid norm so far?
Is it clear that it's not a semi-norm if L and K are not even?
I think so, like,
When L and K are odd, it's not even like necessarily positive, right? Like if you
Yeah.
take A and you make it minus A, like the value negates.
So we took absolute values.
yeah, I did, but I think that doesn't save you. I don't know. Maybe is the answer. I think the answer is no. I remember there's like a paper by Skradov which is talking about something similar to this, even just in the case of like finite abelian groups, like just this applied to Cayley graphs. I think he has some counterexamples showing like the odd versions of. Anyway, that's a vague.
Lucky for us, we can always pick family.
Sure. That is mostly true, yeah. Okay, so I want to try to elaborate on this last point and more generally on this connection to the rectangle norm.
But even if you don't elaborate, it is sort of obvious by definition. I mean, it's indicators of rectangles. So
Yeah, okay, but I care about large
No,
rectangles.
no,
These are like
it's
tiny.
a big rectangle. That's why I asked you before.
I see.
When is it extreme? Let's say when is it biggest? This norm. When everything is one, or when you have a rectangle which is full of one.
Yeah, sure.
Some rectangle it will be much higher when you have a random set of the same density.
Fine, that's what I'm about to talk about. I don't know if it's.
So you will not say more about it. I said it only because you said you are not going to go.
Oh, no, I said I will. I'm sorry,
Sorry.
Sorry, okay, yes, that's what I'm talking about just now. So, okay, so we're talking about this relationship. And I want to talk about an extreme example. So, what do I mean by the grid norm detects rectangles? Well, let's start with just some example. Well, I want to think of like a full rectangle of size delta. So that's like A over here versus B is some random set of density delta. I want you to just believe me that this actually will be pseudo-random. So with very high probability for reasonable parameters, you'll have the grid norm of B is going to be small. Okay, but then mostly I wanted to talk about A. So I'm going to say the grid norm is going to be able to distinguish these two sets. A is just like one full rectangle of size delta. And here's the calculation. So, yeah, so sorry, here's the claim. The claim is that maybe I'll write it like this. So as long as you pick L and K to be like larger than D, then this is true in an extreme sense. Like this grid norm is registering this guy as having grid norm close to 1, even though it has one norm, which is equal to 2 to the minus D. So let me give you the calculation for this point. Maybe I can just here. So the main point here is that this conditions, remember what we have to check. We need to like sample a random grid and then check what's the probability that it lies in the set. In this case, the A is just some product set S times T. Then this condition factors as the product of two like independent events. Like I just need to check if all the X test points lie in S and all the Y test points lie in T. So this just turns out to be some probability of X1 through XL lies in X or S, Y1 up to YK lies in T. Again, we have this factor in the exponent just from the definition. Okay, but then it's easy to say what this is. Sorry, I guess I should, so then this is like mu of S, 1 over K, mu of T, 1 over L, which in this case is very close to 1. So that's starting to reveal the relationship between these two norms with some extreme example. Secondly, I want to give a less extreme example that shows you that even just if your set A has some non-negligible correlation with some rectangle, that it can also distinguish it from randomness. So let me say that here. So this is, yeah, more generally, let me prove this relationship between these two norms. So
It's both, this is not a moving board. The one you're writing on, I don't know if it matters.
I think it would be okay, but be safe, I guess. Why not? All right. Yeah, so I want to prove this thing, which is a more general version of what we just demonstrated above, that the grid norm detects rectangles, which is this relationship. So it's at the very least, this is like showing that the grid norm captures a stronger pseudo-randomness condition than the rectangle norm. So what is the proof? So let me look at A. So this is A, and then I want to just go ahead and look at this rectangle S times T that witnesses this this norm here. So here I have some local density delta, which by my definition of S and T, this is equal to this rectangle norm value. And S and T are both somewhat large. They're both fractional size 2 to the minus P. And then I'm going to do something very simple. I'm just going to not care about any of the points in A outside of here. I only care about the points in A there. So I'm going to write down this calculation involving the grid norm. This is at least A times okay. And then maybe here's something that the next step is something I don't have a very nice notation for, but I want to say that this quantity can be interpreted as some sort of grid norm on the subspace S cross T, okay, with some factor lost in translation. So I'll put that factor out front. It's just a mu S 1 over L mu T 1 over K times the grid norm, I guess, sub S cross T maybe, LK. All right.
That means you are sampling the points only inside S and T.
Yeah. So S and T have replaced the role of X and Y in the original definition. Yeah, that is what I mean here. Okay. And then I just want to use monotonicity. So here I'm just using that this is actually at least one norm on S cross T, which is equal to delta. So that shows this relationship, which is among the two, the easier one to show. But at the very least, it shows you what is the rectangle norm, or what is the grid norm good for? It's detecting rectangles, and sort of something that's useful about it, I guess. No, I'm not prepared to make that point. Never mind. Sorry. Let's see. Any question about this? Either of these two boards over here? Yes, so that's exactly the.
Epsilon means.
But from that way.
Be also.
Epsilon?
Yeah, it would be a power of, not power of logarithm or even.
No, epsilon is always a constant and in all the, yeah, just.
What's the imbalance between L and K? Like, you always think of them as the same roughly, or?
So, for a lot of applications, they might as well be the same. Strangely, for some applications, the thing that we really care about is the grid norm with U2K. So I can say why. In fact, maybe that's worth just saying now. Yeah, I'll write that here. Why not? So that's an interesting point. So it relates to the pseudo-randomness condition that we started with. Yeah, let me remind you of this thing. We had D is the PDF. X plus Y, and I was looking at, actually, for this to be true, I need to lie to you a tiny bit. This is X minus Y, if you don't mind, for this to be right. And then we were interested in this measure of pseudo-randomness, is D near uniform? Okay, now, something that's necessary for this, just by the triangle inequality, is this kind of upper bound condition on D. It's not sufficient in general for this top thing, but it's necessary. But now I can give you a nice interpretation, like what is this thing? And maybe I should switch the normalizations, but this thing is like up to some renormalization, the same as like 1A convolution 1A pth power. This guy is equal to, if we change things around and think about the Kelley graph, some U2P norm of the Kelley graph. Let me give myself a tiny bit more room. Think factor 2 here, but yeah, this is maybe the easiest way to connect the grid norm. If you just want to see very directly why is it relevant to the question that we started with, it's because of this connection, and that answers your question. That actually we care about just the case that L equals 2 even sometimes. I mean, I guess traditionally people care about the case that both L and K are equal to 2. That's like a very classical measurement of pseudo-randomness, like counting 4 cycles, and yeah. I do think probably I should erase this. Is that okay? Okay. Okay, so let me say, maybe that can finally come to what I'm saying is these two main techniques. So some sifting, or at least the results that we can prove. So yeah, let me write this down again. This time I'm going to need to insist that f is some bounded function, and I assume that the one norm of f is at least 2 to the minus d. And we have this opposite relationship between the grid norm and the rectangle norm. This is most roughly some rectangle norm d times L times k over epsilon. Okay. And then the way that you prove this is, okay, if you're familiar with dependent random choice, you can, it's kind of just dependent random choice. I could say a bit more about it, just the algorithm. It's roughly what I described to Yang a second ago, that, you know, somehow to prove this, what do you need to do? You start with some function with large grid norm, and you need to find a rectangle where it has large density increments. So you need to find some subset S and subset T. Essentially, what you can try to do is find some subset S, right? Like maybe draw it like this. So you way that you can try to define S is to take some random columns from A and consider their common intersection. And then that would give you a good candidate for S. If you consider all the random columns, and then you could do something similar for T, and you need to use some sort of like first moment method argument to argue that there at least exists some choice of these random columns that gives you a good rectangle. Yeah, so that's roughly the way that this thing is proved. This is one of the first important points, and then like the second important point is this spectral positivity idea. And yeah, let me write a special case of it that's simple. So suppose I want to think of some bipartite graph as x on the left and y on the right, and I want to say that it's like delta y regular. So it has the same, like it has like a uniform left degree. So this condition, so suppose A is left regular. Really, we can weaken this condition usually, and it's usually like a kind of a small issue to ensure that you roughly have this condition, but this is maybe the simplest way to state what's going on. So in this condition, we have the following happening. So if this A over delta minus 1 U2K is at least epsilon, then we get that A over delta itself U2K. We need to change this parameter K slightly. Then this thing is like almost 1 plus epsilon. And the importance of this second trick is that we're finally able to obtain, yeah, if you read this in the contrapositive form, it's saying that if you have this upper bound control on the grid norm, then it actually gives you this two-sided control, which is the first time we are able to get back some sort of lower bound condition, even though we've only started, you know, from some upper bound condition that looked like this. So putting these two things together, I want to say maybe this is a good thing to quote as like the main lemma in all of these works, and even kind of implicitly in the first one on 3APs, is that, and I can say it like this very vaguely. So if A is spread, this is sufficient for A transport to be near uniform. in a two-sided sense. So specifically, give me some function, some bipartite graph A. It has density delta, at least 2 to the minus d, and also that A has a spread, so it's pseudo-random in the condition we know how to actually obtain. And that it's left regular. Then I want to look at this density function, d of x prime, which I define as this normalized matrix product. So then this thing is near uniform on the product space. Specifically measured by the p norm. Let me.
One is the matrix one.
Yeah. Yeah, this is close to the all ones matrix. Exactly. Great, yeah, so that's what I just want to clarify. Yeah, this is like the result you get by combining these two facts that are both related to the grid norm. And yeah, I guess I want to emphasize that this statement itself, it doesn't have anything, I mean, it doesn't reference the grid norm. It just happens to be the grid norm is the best way, the only way I know to actually connect the hypothesis to the conclusion here is to go through this thing. It turns out to be a useful definition for us, and that these two facts about the grid norm kind of capture the main arguments that we use or that we make about it. So I have said a little bit about how this first one is proved. It's like we give some algorithmic proof of it, as in we can use some dependent random choice to actually construct these witnesses for the rectangle norm. Let me say in the time remaining a little bit about this second point, this spectral positivity, and the role that thing plays. Because I said already why we need it, but let me just say that I kind of want to go back even to the group theoretic picture just for 1 second. We have an argument there that I guess originally I thought it was Fourier analytic, and it turns out to be not really about Fourier analysis or groups at all, just about like positive semi-definiteness. So I'll show you how that turns out. Yeah, so I want to remind you a bit about our, like, the story as a whole, heuristically, as it applies to the group theoretic setting. So we have this density function. And let me, yeah, maybe just to be even more concrete, let's talk about this case, this special case where we're actually just over f2 to the n. this way it's easier to talk about what we're going to try to find. We're going to try to zoom in somewhere to make things pseudorandom, and specifically, we're going to zoom in on some affine subspace in this case. And remember, our idea is that like if this thing is not near uniform, then the reason that should be the case is that we can identify some like structured set to zoom in on. So we have some affine subspace V here, and we zoom in here. So remember that, yeah, this was like what we imagined should be happening. This is what we'd like to happen for the plan to make sense. So I want to point out something that could happen here, which would just kill the plan outright immediately, and it has almost nothing to do with even like the structure you're trying to find, is like maybe your PDF just looks like this. Like you have some bad set that's larger than 2 to the minus p. Okay, but then it's your PDF is like uniform on the complement of that set. And then this thing here, it's not a density increment by some constant epsilon. It's like some exponentially small thing that doesn't help you at all. Okay, so somehow if D looked like this, then we would have no plan. Even if like it, yeah, even if this was a subspace, like which would be a lot. I mean, that would be a lot to try to prove, but even if it was true, it would be not helpful to have this density decrement on some structured set.
Just this is already spread now.
No, well, sorry, we're asking if D is near uniform.
Yeah.
And it's not, because I have some bad set that's too large, right? Yeah. So it's not near uniform, and yet I have no plan. Like my plan was to take a density increment somewhere, but there is just no substantial increases over 1 here. And I want to say, like, so what is the role of spectral positivity in this context is just that it rules out this picture. Like it just says that self-convolutions just can't look like this. Like if you have some density function and it's substantially below 0 somewhere, then it actually has to be substantially, or sorry, below 1 somewhere. It has to be substantially above 1 somewhere. Specifically, as measured, like say, by any p norm. So this is what I'm saying is true. So D minus 1, lower deviations are never larger than the total amount of upper deviations. And how do we prove this? Well, the proof, once you've decided on the idea, is actually very simple. This is all this is saying is, this is equivalent to that D has non-negative odd central moments. That is, if I wanted to hold for all odd integers p, which I would be happy with, then it's equivalent to this, that I write down this expectation. And then just for any odd integer p, we have this inequality that this is at least 0. So that would be sufficient for this. And then, yeah, so what is the reason this is true? It's sort of very clear if I just write it out explicitly using, I guess, yeah, let me just write out the calculation. It's some Fourier analytic calculation, but remember, D is a density function, so it's trivial Fourier coefficient is 1 just by normalization. And then it has this representation remember the definition of D was the convolution of some set A with itself. So it's like this expression here involving only non-negative Fourier coefficients. So what happens if I just look at this quantity explicitly? Well, then I just take out the one from this this leading one here, and I'm still left with some function inside the peak power that has only non-negative Fourier coefficients. And I guess what I'm trying to say, I mean, the exact, well, let me just write it out, might as well. So the exact expression here is not so important, but the main point is just to observe that there's only non-negative terms present. So in a sense, we've just given like some sum of squares proof that this odd central moment is non-negative for any p. Okay, so that's what I'm calling like this technique, spectral positivity, in the context of, in the arithmetic case, it's just verifying that if you have some density function that's not uniform, it actually has to be to have some problems in the upward direction and not just the downwards direction.
Why did you use it even odd?
Oh, I don't use it. I'm saying it's only useful for p, which is odd. Right. So get this thing on the top right.
Yeah.
Okay. Yeah, it wasn't necessary though. And then, okay, so what's my point now is that roughly the exact same calculation can be used in a more general setting where you just have a density function over a product space, which is PSD as a matrix. So here, let me say I have some density function D over some product space. And it's a density functions. And then also, so I need, this is related to this regularity condition, but like I'm assuming that its top eigenvalue is 1. Okay, so as long as that's the case, then E has this representation as some, maybe I'll write it. I've lost. So let me describe it like this. It has some constant term 1 in the front, plus some terms coming from its like eigenvalue expansion. So it's equal to 1 plus some non-negative combination of some rank 1 functions. And the main point is just that the same calculation will just also give you a sum of squares proof that D is has non-negative odd central moments.
Lambda negative.
Yeah. That's necessary, or that's important, sure. Yeah. So what's happening is just roughly the same reasons as before, you just expand all these terms and see because of the positive semi-definiteness structure, you're only getting non-negative terms in the end, and then that proves this inequality. Yeah, I guess one second way to interpret this, if you like, there's this result. I mean, it's kind of this, the proof of it is roughly the same difficulty as just writing this out, but like it's called Schur's lemma that says that the element-wise product of some positive semi-definite matrices is again positive semi-definite. So that's another way to interpret how this proof is going. What's really happening is we're applying Schur's lemma, and then taking like the inner product with the all ones vector at the end, if you like. And that's what's giving you this inequality. Okay.
The fact that you have a positive part that's as big as the negative part, why should it be in a subspace?
Yeah, so that's unrelated to that second point, right? Yeah, so I agree. It doesn't help us but it helps us. So yeah, if you want me to, maybe I'll do it over there. I have understood. So you're right. So in fact, you can kind of imagine the entire argument all at once as like chasing the witnesses of this deviation from one. So let's imagine how this goes. So we're looking at A convolved A. To begin with, we have this bad set Z of points that are too low. So the first step is sort of to use this positive semi-definiteness argument to say that there's some set Z prime of upwards deviations. Currently, we have no structure on Z prime. It's just a large set. I mean, we began with a large set. Now we just have a large set of upwards deviations. And then, like, what is this telling you? One thing that it tells you is that this P norm is large. For some reasonable value of P, it's like 2K over epsilon, I guess. Okay, but now this is saying that some like grid norm of A is large, so we can continue for other reasons. And yeah, I guess I'd like to draw the picture in the arithmetic case. In some sense, what do? We find a rectangle density increment in the graph-theoretic view, which in the arithmetic view corresponds to this. We find some like witness S convolved T that witnesses the location of this deviation upwards from one. Okay, so that's like kind of the second part, and then the third part is the part that I haven't talked about at all in the talk. It's this like translation invariance step, this thing that was more standard in the field already, which is saying that if you have this situation, then you can actually bootstrap this into finding some subspace witnessing this deviation upwards. So this is like the third step. That's only is like the only part of the whole argument that is not combinatorial. It's really about the group structure.
But in Z mod n, you don't need it.
In Z mod n.
Yeah, here it talks about x to the n, and this is the subspace.
No, sorry. In Z mod n, you get something else. You get like a Bohr set.
Both. Yeah.
Sorry. You need more, I guess. I just okay. So the F2 to the n.
Arithmetic structure.
Yeah, you need some arithmetic structure, and that's what this third tool, like the Frutzis lemma variants of it, give you this last point. Okay, so yeah, that's everything I planned, I think. Thanks, everyone.
So the dependent random choice step, or what you call sifting, it works very well in the quasi-polynomial regime, I guess, because you can take L and change D to some polynomial in D. But let's say you have some problem that is in the polynomially sparse regime, then I guess the sifting lemma you can only apply with L and K constant. To know if there are something useful to be extracted from there, or like for sparse problem, do you expect that?
So I at least know something very interesting that's new. I guess it's going to be something I'll talk about a little bit next time. A new result due to Shahar and his student and another student at UT, so they proved like they got quasi-polynomial bounds for corners over certain groups, like over SL2Z. or sorry, SL2P. And in fact, something that would like the main, well, okay, there's a couple technical challenges, but one of the main technical challenges was exactly related to what you described, is that you need to do sifting to connect these two, measurements of pseudo-randomness, but for F, which is very sparse. So they have a plan to do it, but it's for a function which is, it's sparse in the whole space, but it's actually dense inside some very pseudo-random container set. So it's sort of like a dense model theorem type situation where they're showing that you can do sifting in this setting and you only pay some factor D, which is related to the density inside your container set, not inside the whole space. So I think this is the only example I know of overcoming this difficulty, but yeah.
Sifting refers to taking the columns and taking the intersection. What does the word refer to?
Fine. Yeah, I should. Okay, the word is has a very good picture in the arithmetic setting only, which I guess I should have talked about. So, show you. So it's some idea that I guess, yeah, we talked about this dichotomy we're trying to prove. We're trying to show that something is either, pseudo-random or has some additive structure. You can imagine that the hard case is like some mixture of the two. Like it's has too much structure to be pseudo-random, but like the structure is kind of small. It's like some small planted additive structure inside a larger ambient random set. So let's imagine that, like, say you're in F2 to the n, and you have some medium-sized subspace. So A is some medium-sized subspace plus some larger random set. So just a bunch of points out here. Okay, and then the idea is like somehow it's important for us to actually locate this subspace, even at least in this simple example. You'd like to have some plan that like locates it automatically. So what's something you could do? Well, you can do the following, and it works reasonably well. You can take some like random additive shifts of the whole set and consider some like A intersect A plus S1, maybe to make it more suggestive. A plus Y1 intersect A plus Y2. And you can look at like what you'll get. Like what will you find by looking at this intersection? So maybe the point is that you'll locate like some of this subspace, but then none of the dust, like that will just all go away. And then you found some of this like planted additive structure inside. So that's the reason for the
Does this mean that you can write your like whole 3 AP proof like without ever saying the word Fourier transform?
That is I'm actually very interested in that question. It's like a really technical question that's hard to honestly say yes to because of some results due to Sanders and regarding Bohr sets. So let me, depends on if people would like, maybe I should take it offline. It's an interesting, I have an interesting answer to this, but it would take me like 5 minutes.
Well, can you, but before that, can you say it honestly if you were working over F3 to the n?
I don't think that even helps. Okay, so what would it require to do it honestly? I can't even say the algorithm without, because what is a Bohr set or a subspace? Like really, it's like the set where some characters are roughly constant. Now, it's possible that I could say the algorithm, like I need to write to describe the answer to this question. Okay, fine.
No, it is 40. Until 1:30. So okay.
Oh, it's until 1:30. Oh, I thought
Take food till 1.
I see. Oh, I thought it's until 1.
No.
Oh, no. Okay.
One may stop having food, but you can still go in and try to.
And then like, okay, maybe.
Okay.
People, they're buying me food right now.
Can we buy for everyone?
Sure.
Now Zander is stressed.
It's okay. Okay, so first, let me just tell everyone what a Bohr set is, just because I feel like it's unfair not to do that. It's fairly simple. I guess I'll say inside cyclic group only, just for simplicity. So it's like, it'll be the set of points where you have
Really, I mean, this actually to the end from the simple, you will just talk about subspaces, or you want it from.
I don't think it would. So there's a reason it would be, but
No, just notation wise, I don't, yeah.
no, I think,
Okay,
okay,
fine.
I mean, this is, I'm almost, okay.
Yeah.
Okay, so this is the definition of a Bohr set. You can see how it kind of generalizes a subspace in some Fourier analytic sense, that we're just looking at some set of characters. This is like a rank R Bohr set of radius rho. We're looking at the points where this character is close to 1. Okay. Now, for the whole argument, we only really use something very simple about Bohr sets, which is a combinatorial fact. It's like that they are translation invariant. So specifically, so here's just a fact about Bohr sets, that they're like, I guess for any choice of epsilon, there exists some subset X such that yeah, okay, so there exists some large set of, maybe I can make this even simpler, like the, well, if you like this second condition better, I think it's a little simpler because it's something you test for each point X in X. It's B is nearly translation invariant to the shift by X. Okay, and then so this combinatorial statement is saying that there's like a lot of these directions in which B is almost translation invariant too. And so you could actually try to frame this whole argument by saying, let me just take density increments onto translation invariant sets, like just use this definition, right? It like almost works. I tried to work it out with Thomas Bloom at some point, and there's some like technical annoyances that I don't know how to, like, I think the statement is probably true, but the only way I know how to prove it is to like go through Bohr set, is like to say that actually anything that looks like this is like a Bohr set. Something you could do with Bohr sets is you can dilate them to get a smaller Bohr set. And yeah, so I think it's an interesting technical challenge to actually do this, but I don't know how I can do it right now. No.
Okay, so thank you very much. We can have you back.